All right. Hello, everyone. Thanks for joining the Petroleum Engineering course by SPE BHOS. I'm Toral Tyrov, the Senior Advisor of the team, and I would like to welcome all of you who have joined our previous session or all of you who are joining right now. So please do not forget to tune up to our course in the Telegram group, as that's the way in which we are communicating with our followers. So, and thanks to Javid Shiriyev for agreeing to this, to presenting in this course. He will be sharing his valuable experience with us. And he's also a professor in our University of Baccalaureate School, as you have already been mentioned about from the previous session. So, welcome again to the second section of this course, and we will be starting, if you are okay with this as well, Javid, teacher.
Yes, yes.
All
Thank you
right.
very much for the introduction. And
Sure.
last in the last session, I just briefly mentioned about the scope of these classes, but this time I'm going to go into a little bit more details, of course, and we are going to show basically the overall um, objective of this session is to develop a first version of the flow model, which will be able to simulate multi-phase and transient problems and also multi-dimensional problems. Okay, so we have the three objectives here: to simulate the multi-phase flow, to simulate the basically it means that we are going to simulate the transient problems, and also it means that we are going to have, like, it's possible that we have the 3D domain, like it's multi-dimensional domain. But like, in order to keep it simple and in order to understand the steps, we should like, I will break it down into several steps. In the today's session, the aim is to develop the single phase steady state solution for one-dimensional problems. Okay, so that's the first step. And if we successfully complete that step in the today's session, next time we are going to pass to transient problem. Instead of solving the steady state solution, we are going to solve the transient problem, again one-dimensional. And then in the later step, we are going to switch to single phase transient problem, this time multi-dimensional. So we are going to add the YZ axes as well. And for all simulation, we are going to work with the Cartesian grid system. And later, we are going to switch to the multi-phase, transient, and multi-dimensional problem, solving the multi-phase, transient, and multi-dimensional problem. So these are the steps that we have in the scope in this session. I will go over the derivation, and meantime, when I'm presenting, I will be using some of the packages that I just created in the GitHub. So it will be important to to download those codes that we have in the GitHub. So I'm going to share the screen with you, and I will show the link as well. So this is the post by module that we have only computation tool here. I will explain what we have here inside. This is the finite difference solver for now only. For now, it's only finite difference solver. Later, it may have the finite element solution as well. But at this stage, for the scope of this session, we need only finite difference solver, and it contains it. And I will update it as we need to switch to the multidimensional and transient problem. So this is the link I'm going to share with you. If you want to download this, you just like simply go go to the file, and then download it. Okay, I will show you how to do it, and I'm sharing the link with you as well. I'm going to send it to the chat box. So let me log out from here. So if you just click on that link, then you will be directed to the BHOS Pi module, that where we have only computation pi. and that you can just download by downloading the zip, and then you will get the computation file. Okay, I have it here on my folder, so I will be using this computation file. And now let me go over the derivation steps, that the important derivation steps that we need to understand before we implement the finite difference solution. Like basically all the simulators that we have in the petroleum engineering for the reservoir simulation purposes are based on the three main steps. First, we need to understand the general principle that we are implementing. This is something that we are covering in the fluid mechanics class as well. For those of you who are attending the fluid mechanics class are familiar with the subjects. So the first step is to understand the general principle. Second step is to understand the constitutive equation. And third step is to understand the equation of state. So for the general principle, as you know from the general mechanics courses, we need to conserve the mass, okay? And we need to conserve the momentum, and we need to conserve the energy. And in the reservoir simulation, mostly we are using the conservation of mass only. And then we are incorporating the our constitutive equation, which is a Darcy equation, and then for the Newtonian fluids, and then we are implementing the equation of state, which is the single like equation of state. For example, for the oil, we can assume the slightly compressible model. And if we add all those equations together, we're going to get the final form of the diffusivity equation. And that diffusivity equation is very common in all engineering. It's not only petroleum engineering specific. So like if you have a heat flow problem, or if you have a fluid flow problem like we have in the reservoir, you'll get the final form of the equation is very similar. And that equation is known as the heat equation sometimes as well, okay? And if you are solving the steady state of this problem, then it's even simpler. And it's generally known as the Laplace equation in the mathematics. If it's not the zero, if we have the basically two hand side of the equation, left hand side is the Laplacian, and if we have the right hand side equal to zero, then this equation is called the Laplacian and Laplace equation. And in the second case, when we have the right side, which is not the zero, but it's some other constant, or maybe function, which is dependent on the x, like the coordinate system that we are dealing with, then it's possible. It's called the Poisson's equation. Okay, and then if we have the time-dependent derivative on the right-hand side, then it's called the transient problem. Okay, so these three types of problem that we need to understand. For the Laplacian equation, for the simple geometries, we have the analytical solution as well. And for the Poisson equation, even like for some complicated scenarios where we have the analytical solution as well. For transient problem, for simplified geometries, we have the analytical solution as well. So whenever we are doing the numerical computation, it's really, really important to understand those analytical solutions in order to benchmark your numerical simulation. If you like, you can use your numerical simulator only once you validate it with by comparing to the analytical solvers that you have. And yes, as Total mentions, if you have any questions, just let me know. Okay, stop me, ask the question. Otherwise, there's no point of me continuing to talk if you have something that you didn't understand at the initial steps. Okay, ask the questions whenever you want. Let me go over the steps again. Like this was the general overview, like verbal overview. Now let's go over the contingency equation that we have for the fluid flow through porous media. Now in the fluid mechanics classes, when we are dealing with the general principles, we are focusing on the conservation of momentum because most commonly in the flow problems, in the fluid mechanics, we are talking about the pipe flows. But in the reservoir engineering, we are mostly interested in the fluid flow through porous media, which is a little bit more advanced topic than the conventional fluid mechanics subjects. I'm not saying that those equations are simple, but I'm just saying that this is more, this is not mostly covered in the conventional fluid mechanics classes, but it's mostly covered in the reservoir engineering classes. So this, like in all of the mechanical, if you are taking any mechanics courses, if you are dealing with the elements that's formable, then you have probably heard about the control volume. And control volume is very small size cube, which has the finite dimensions. And we are implementing all the general principles on this model, on this small model, and then doing the integration, we are getting the final form of the equation. So basically, in this control volume, if you are talking about the conservation of mass, and if you are looking at the only x direction, okay, if we are not dealing with the y and z directions, then we can assume that there is a flow from the left-hand side of the control volume, and there's a flow in from the left-hand side, and then there is a flow out from the right-hand side. And if there is no storage in the given control volume, then the mass out minus mass in should be equal to 0. Okay, that's the conservation of mass. And then if you do all this multiplication, taking account the volume of the control volume, and then take the ratio, like divide it to the total volume of the control volume, we are getting this form of the equation. And then if we are taking the derivative of this equation, then we are going to get the this equation. Okay, this is the equation if we are dealing with only with x-axis. If we do the same thing for all directions, y-z directions, then we are going to get the same derivatives for the y-z directions as well. So it's basically just summation on the x, y, z direction. And that equation will be simplified to this form. If you are dealing with the conservation of the mass when the fluid flows through porous medium. Okay, this P is the porosity, rho is the density, and V is the velocity, flux basically. And its unit is meter per second, like SI unit is per meter per second. And we have on the right hand side we have the derivative with respect to time. Now let's like for today's scope, we're talking about the only single phase flow. Okay, and that's why I'm stopping here, and then I'm switching to the constitutive equation that we have. So we talked about the general principle, and we said that in reservoir modeling we are only considering the conservation of mass, and the final form of the conservation of mass is given here in this equation, which is 1.7. Now, if we are talking about the constitutive equation, the constitutive equation in our case is the Darcy equation that we have, which first was derived based on the experiments that the Darcy carried, but then it's also validated with the derivation. Some theoretical derivation can be shown from the Navier-Stokes equation as well. Okay, so like generally the flux in this constitutive equation, the flux is correlated to the permeability of the rock. In the single phase flow, we are talking about the absolute permeability only, and then it's correlated to the fluid viscosity, and then differential of the potential that we have in the given system. Okay, so this is the generalized form of the Darcy equation. And this potential is correlated to the, it's basically, there's a linear relationship between the pressure and potential. It's just, we're adding the gravity as well, gravitational, hydrostatic pressure as well. Okay. So
Javid
yes.
teacher, sorry for interrupting, but we've got a question in the chat box. Rasul Amirov asks, what is phi in the equation?
Okay, that's porosity. In the previous, when we were talking about the conservation of mass, P is the porosity. Okay, but here this symbol represents the potential. Okay, now okay, Rasul. Now if we include, basically, if you look to this equation in the Cartesian coordinate system, and if you assume that we have our gravity is in the z direction, then this equation can be written in this form. Okay, in this general form. In the first form, we are writing everything in the x direction, assuming that there is no gravity in this direction. Again, the same thing for the y direction. And lastly, we are talking about the z direction, where we include the gravity. Okay, this is the form of the constitutive equation that we are going to use for now. Okay, and in this session, we are only talking about the Newtonian fluids. And Newtonian fluids obey this constitutive equation that we have that's shown here. Okay. In general, we can have Darcy equation for non-Newtonian fluids as well, but it's out of scope for now. Okay. So it can be numerically, like numerical solvers can handle those scenarios as well. Okay. Although it becomes a little bit nonlinear, the problem becomes nonlinear, and I mean, it's not robust all the time, but it can still be handled for the non-Newtonian fluids. But for now, we are only focusing on the Newtonian fluids, and this Darcy equation is the constitutive equation that we are going to use for our problem. Now, talking about the equation of state, that's the last thing we need to know for our single phase solver. So let me open the proper file for that equation of state. Now, we are talking about the slightly compressible fluid. Okay, if we have the incompressible fluid, basically we are solving the Laplace equation, and in this session we are going to see the Laplace solution for the given one-dimensional problem, one-dimensional domain. Okay, so if we have the incompressible fluid, our diffusivity equations becomes Laplacian equation, Laplace equation, and that Laplace equation, the solution of that Laplace equation is going to be shown in this session. Once we have the slightly compressible fluid, our problem is the full transient problem that we have. Okay, this is not the final form is given here, and this is the diffusivity equation that we are going to solve. Okay, for the single phase problem that we have today, we are going to solve the Laplace equation, which is the solution for the incompressible fluid. In the next session, we will try to solve the slightly compressible fluid, which is the full diffusivity equation shown here. Okay. For the incompressible fluid, we have the Laplace equation. For slightly compressible fluid, we have the diffusivity equation shown here. And this eta is the hydraulic diffusivity, which is defined as shown here. And this K is the permeability, phi is the porosity, mu is the viscosity, C is the total compressibility. Okay. So these are the three main equations that we need to know in order to get the final form of the equation. Okay. Now, let me now this is the final form of the equation that we are solving with the we will try to solve by steps. Okay, this is the final form of the solution equation for the single phase flow. Okay, for several sessions we are going to talk only about the single phase flow, and in this single phase flow we are going to assume that we have the incompressible fluid, and incompressible fluid means that rho is constant. And if we take out this density from this equation to the left hand side, and the same thing for the right hand side, then those rho's are going to cancel out. And we know that our porosity doesn't change, so it means that this side of the equation is going to be zero. Okay, which means that the Laplacian, and if we assume that we have the constant viscosity and constant permeability, it's going to be only Laplacian of the potential. And basically, Laplacian of the potential is going to be equal to the zero. And then if we implement the boundary conditions accordingly, then we can solve the problem. Okay, that's something we are going to do now. In the case when we have the slightly compressible problem, this right-hand side of this equation is not zero, and we need to consider the time changes as well. Okay. So the steady state solution that we are going to get for today's session is shown in this graph. It's shown with the yellow line that you see here. We may have like two types of the boundary conditions on the well that's something we told in the last session as well, in the introduction session as well. So we can have the constant flow rate solution, and we can have the constant pressure solution for the wellbore. And at the outside of the boundaries, we are going to have the Newman boundary condition, which means that the pressure gradient is going to be equal to zero at the boundaries of the reservoir. Okay. Now, this graph is shown for the radial direction, but in today's session, we are going to solve the only one-dimensional problem, which means that we are going to solve only for the x-axis. Okay, we're not solving the radial problem yet. We are only solving the one-dimensional and Cartesian problem. Now, if you do the same thing like numerically, so this is the equation that we were talking about. Okay, if we have the well in the given reservoir, then we need to include the source term in the equation, and source term is usually shown with the m dash. Okay, we're going to talk about how to include the wellbore in our model as well. It's just a slight modification to the overall matrix that we are going to get at the end. Now, the other thing, for like we have the variable permeability for the numerical in the numerical solver. That's okay. But in our case, we are assuming that like basically most of the problem, we have the anisotropic permeability tensor, and it's going to be full tensor, and it's going to be symmetric as well. But like most of the time, the problem can be simplified to be diagonal dominated, and we will have only diagonal entries. The other entries are going to be zero. So if we rotate our coordinate systems accordingly, we are going to get the direction where we have the permeability values only at the diagonal. Okay, so that's why the general problem can be solved with assuming that we have the permeabilities only changing in the x direction, y direction, z direction. Okay, we are not going to look at the off diagonal values. This is the case for this problem, and for our problem, if you are talking about the permeabilities. But one thing we are going to do is we are going to assume that the permeability is constant, because we are going to compare it to the analytical solution that we have. Okay, it's going to be probably the next in the next session, because in this session we are going to solve the Laplace problem. The Laplace problem is the permeability is basically since the right hand side of the equation is zero, permeability, if we assume that permeability is constant, it's going to cancel out by zero. And then we are going to have only pressure term. Now, the next thing is basically if we get this final form of the equation, this is the diffusivity, the eta term that we have shown. Okay, hydraulic diffusivity term. And now, in the case when we are solving the 1D diffusivity problem, when the right-hand side of this equation is zero, then we can solve this. Basically, this equation is going to be a line, okay, straight line, and we can find the analytical solution easily. We will have the analytical solution, and we will have the numerical solution, finite difference solution as well, and we are going to compare the finite difference solution and numerical analytical solution as well. Okay, so in the case when we have the this general equation, general diffusivity equation in the one directional Cartesian domain, then we can implement this boundary condition to get this analytical solution. So okay, so in this session we are going to have the analytical solution of the straight line, which in the case when we have the steady state solution, this is the solution that we are going to get, because when we have the steady state analytically, it can be shown that the pressure is going to be just a straight line. And when we have the time transient problem, time increasing problem, time changing, time dependency in the problem, then our solution is going to be looks like this, depending on the time when we're plotting this pressure in the given domain. And this is the general equation, general analytical solution that we are going to get for the transient problem in one dimension. Okay, so today's session we are going to compare the analytical solution is going to look like this one, steady state solution. Okay, and in the next session when we are solving the full transient problem one dimensionally, we are going to compare our numerical result with this equation. Okay, now let's talk about how we're going to generate the matrices in order to get the like basically to get the the finite difference solution. So first, given the problem, given the left and right hand side of the problem, we need to discretize the domain, okay, and then generate the number of elements, okay. And what I'm calling the number of element is just the like it's one-dimensional. Like you can assume it has to be a straight line, okay, and it has a certain size. It has the center, which is the mass center, and it has dimensions. It has size. It has the ID, given ID in the given domain, based on the discretization that we are having, and we need to locate all this information in the mesh. So for any kind of the numerical solution, that we need to have mesh. Okay, so the mesh is something that we need to generate. Okay, once we generate the mesh, we need to generate the general matrix, the A and B matrices that we are going to solve. Third, at the third step, we need to implement the boundary conditions, okay, and then after applied with B. Now, in the case when we are solving the steady state problem, when the right hand side of this equation is equal to 0, then it simply means that we are going to solve it only once. But when we have a time dependency on the right hand side, it means that we are going to solve the same problem multiple times based on the time that we are solving this problem. Now let me open the numerical part. Now, when I'm talking about the discretization, this is something that I'm imagining. Okay, let's say that this is the x0 is the left-hand side. Okay, problem. For now, I'm assuming that I have 7 elements. Okay, and I have 8 nodes. And in Python, everything starts from the 0 indexing. So I'm starting with the 0 index as well. Okay, those are the elements with the center given with the black dots. Okay, I have the U, which is a representative of the pressure. Okay, because we are solving the Laplacian equation, and Laplacian equation in one dimension is given with this equation. And like we showed that for steady state problem, diffusive equation simplifies to this form, and this U is representative of the pressure. And on the left-hand side, we can implement the Dirichlet boundary condition, assuming that we have the constant value of 200 at the left-hand side. And on the right-hand side, we can assume that we have the constant value of, we can assume again Dirichlet boundary condition, assuming that we have the value of 50. Now, if you are solving this this analytically, we will see that it's just a straight line connecting the 250 on the XY graph. Now we are going to solve it numerically, and we are going to play with this 0 just to make sure that our analytical solution and numerical solution matches as well. Okay. Now this is the discretization. Okay, we need to generate a mesh in the code. It should generate a mesh. Basically, we are going to input the number of elements, and it's going to generate the mesh accordingly. And the smaller the sizes of the elements, the higher accuracy we are going to get. Of course, the computation time will increase as well. So number of elements defines the number of unknowns that we are going to solve. Okay. So if we have 7 elements, it means that we are going to solve 7 U values at the given domain. Okay. And we are implementing the boundary condition at x0 and x7. There will be some like these are the calculations. So there are some necessary calculations that we need to know to do in order to generate the full matrix. But all those calculations can be done in the mesh generation. Okay. So all this information can be stored inside of the mesh. And in all our calculations, we are assuming that we are solving for the unknowns at the center of the grid. Okay, we are not solving at the nodes, we are solving at the center of the grid. Okay, and it's not necessary that we'll have the same size nodes. It can be different. If there can be differences in the sizes of the elements as well. It's not important that they are constant. Now, let's talk about the boundary condition. Dirichlet boundary condition simply means that we have the constant value of the u at the given boundary. Newman boundary condition, it means that the gradient of the u at the given boundary is equal to some function. Okay, and that function is just it can be just a value, a scalar value, or it can be a function which is defined for the boundary. Okay, it should be a value. Okay, at the end it should be a value. Now, Robin boundary condition includes both the Dirichlet boundary condition and Newman boundary condition. So, to have the generalized solver, we need to combine this Dirichlet boundary condition and Newman boundary condition. So, that's why we are going to implement the Robin boundary condition, and we need to define the coefficients for the Dirichlet boundary condition, which is B0, and coefficient for the Newman boundary condition, which is given B1. Okay, the gradient of the u with respect to x multiplied with the Newman coefficient and plus u multiplied with the Dirichlet boundary condition is equal to some scalar value or a function which is defined for the boundary. So this is the general equation of the boundary condition that we are going to implement. I said I have this computation script. Let me go over this computation script. So this computation script contains all the necessary few functions that we are going to use. So this is one of the solvers is the finite difference solver. Okay, and this finite difference contains the we should input the mesh information. Okay, and then it's going to still working only for the one-dimensional problem, but we are going to extend it to make it multi-dimensional. So
dimension problem. Sasus Omos.
okay, so in the central difference, inside of the central difference, it takes basically the central differential of the given function. Okay, let's say we have the u values defined at the several different points of the given domain. Then we can take the calculated central difference by using this central function. Okay, and then we can implement the boundary condition. And that boundary condition requires the knowledge which nodes are the knowledge of the boundary grids. Okay, we need to have the information about the boundary grids, index of the boundary grids, and also we need to have information related to the neighbors of the boundary grids. And also we need to know which boundary condition we are going to implement at those boundary points. Okay, boundary grids. Okay. So this is something that we are going to use in order to calculate basically calculate the Laplace equation in the given one-dimensional domain. Now, if please download it from the GitHub from the link that I sent you, and we are going to solve it. We are going to use it in order to solve the one-dimensional Poisson problem. And in the case when we have the right-hand side equal to 0, it's a Laplace equation. Okay, this is my cheat sheet that I'm going to have, but we are going to write this script together. Okay. Now I'm starting a new script. And I'm saving it as a test. Okay, this is a test because I'm going to compare the analytical solution and finite difference solution as well. So that's the reason why I'm calling it test. And I should mention what type of test it is. So for now, I'm solving the one-dimensional Poisson equation. So I'm just naming it as a 1D Poisson. Okay, this is test 1D Poisson. and I have the analytical solution not inbuilt, but I'm going to just copy paste the analytical solution as well. An analytical solution you can derive by yourself as well. It's straightforward. You can just take the if the right hand side of the equation is equal to 0, you can just take the derivative and you'll see that the solution, analytical solution, is a straight line connecting the boundaries if we have the dirichlet boundary conditions defined at the left hand side and right hand side. Okay, so now first thing first, we said that we need to create mesh. Okay, and obviously we are going to use the numpy for the generation of the node point. Okay. So that's why I'm importing the numpy. And then the first thing first, I need to generate mesh, and basically this is going to be an object about the mesh, and it will contain all the necessary information regarding the nodes, sizes, center of the grids, and also it will contain the IDs of the grid. Okay, let's say that I'm creating an object of the grid. So this line is going to just create the empty object of the empty class of the grid. Okay, and I'm going to fill all the necessary information. Okay, if I have created such an, let's say I'm going to stick to this discretization for now. Okay, so basically it means that I need to have the, if I have the like the first thing I need to define is the number of elements I'm going to have. Okay, and this number of elements is given to be 6. Okay, 7. Sorry, if you count, like, since we start from the 0, it's going to total number of unknowns, total number of grids is going to be equal to the 7. Okay, let's say grids number is equal to 6. Again, 7. Sorry. Now the second thing, I need to have the IDs for the for this discretization. Okay, so it should start, this IDs should contain all the IDs that I have for this use. Okay, it should be 0, 1, 2, 3, 4, 5, 6. Okay, and that ID can also contain information about the neighbor cells as well. Okay, for the U0 it can include U1, and for U1 it could include U0 and U2, and for U2 it will be contain the U1 and U3. And for the elements where we have only for example, for the U0, we are going to have U1 only, which means that then we will understand that since we have only 1 and 3 at the U0, it's a boundary point. Okay, so we can make it automated, or we can still make it simple. So right now I'm going to assume that I'm going to only have the ID. I'm going to have only IDs for the every given unknown, which is the center of the grid. Okay, and that grids can be, the IDs can be generated by using the numpy arrange.
Teacher, sorry for the interruption, but we have a few questions in the chat box asking about the py file, a py file developed, downloaded from the GitHub.
Nothing happened when I run py file. That's okay. I mean, nothing should happen when you run the py file. Just put your the computational Python file in the folder, and also try to generate the same script that I have here, test1d poison. Okay, if you want, you can just name it the same, and do not change the name of this computation. Okay, for now, like basically make sure that you have the computation and test1d poison in the same directory. Okay, doesn't matter where you have it, as long as you have them in the same directory, it should work. Nothing happened when I run py file. Python, please download the computation, and if it doesn't give you any error, it should be fine. Okay. And Leofort Caribbean file is not running. It's like what error it gives you. Okay, Typhoon. Therefore, So what's the error that you're getting when you run the script? Total, can they talk as well? Can they open their microphone? Total. Got through. Okay. Okay. Okay then. I'm continuing. No, we can't. This okay. Rasul, is it restricted? What's the reason? Why is their microphone is restricted? Total.
Yes, I will deal with it right now.
Okay.
Okay, the permission is granted.
Okay. Whoever wants to ask question, just try to open your microphone, and if you have any problem, just write it in the chat box. Let's make sure that we can run the script today. Okay, Shashwat, I didn't got any error, which is, I mean, it's fine. I mean, everything works well for you then. Okay then. So I'm continuing. If you have any question, just let me know. Okay. I had this cheat sheet open. That's why I couldn't see the chat box. Now I'm going to make sure that I see the chat box as well. Okay. Now, so we can create those IDs by just using this numpy arrange function. Okay. And the starting point is going to be 0, of course. So that's why it's not a option. It's not a must entry. Okay. You see the arrange. We have the rectangular brackets, which means that it's optional. Okay. So since it's by default, it's assuming that it's 0 start point. So I'm not entering any starting point. I'm just entering the stop, which is the must entry, and where should it should stop. Okay. And I'm typing the grids number. Now, if I run this script, for running, I'm clicking F5 and then enter. Now, if I check the grids number, I will have 7. And if I check the grids IDs, I'm going to have 0, 1, 2, 3, 4, 5, 6. Okay. And those are the index values of the unknowns that we have. Okay. 0, 1, 2, 3, 4, 5, 6. Okay. Those are the unknown points. Okay. Next thing I need to define is the node location. Okay. And those node locations are given with the, like, let's say I'm defining the x0. Okay. And x0 is the node point. Let's make sure that it's clear. So I'm typing n, just make sure that this is the x value of the node, and I'm looking at the left boundary, and which is 0. Okay, and for the right boundary, I'm going to have 7. Okay, those are the values that I have here. 0 to 6, and my x0 is at 0. Okay, x7 at 7. Okay, now if I want to generate the x coordinates of the nodes, I will just type grids nodes. Okay, and it's going to be, I'm going to use the linspace of the numpy. Okay, and my starting point is going to be x0. End point is going to be the x1, which is the node points, which are the node points. Okay, and then here, everyone can unmute now, but please make sure to stimulate if you're not asking question. Okay. So I have the left-hand side of the domain and right-hand side of the domain. Okay, and then I need to make sure that the number of nodes I'm creating is correct according with the element that I have. And number of nodes is always one larger than the grids number. Okay, so element number plus one is going to give me the nodes. Element and grids I'm using interchangeably. Okay, for now it means the same thing. And so I'm basically going to add the grids number 1. So if I run this one, I'm going to get grids nodes is going to be 0, 1, 2, 3, 4, 5, 6, 7. Okay, those are the node points of the given domain. Okay, between the 0 and 7. I have 8 nodes, 7 elements, and my number of unknowns is equal to the number of elements that I have, because I'm implementing the finite difference at the center of the center of the element. Okay. Now I want to learn the size of the every grid, because I know that, like, although for this simplified case I have the constant delta x value, but I want to make sure that when I have the grid size differing than the different grid sizes, I will be able to use the same solver. Okay, so I'm just for now I'm calculating the sizes, and for that I'm just looking at the grids nodes. Okay, I'm taking the second boundary of the nodes, okay, and subtracting grids minus 1. Okay, I'm taking the basically I'm taking the x first. I'm taking on the x1, x2, x3, x4, x5, x6, x7, and subtracting x0, x1, x2, x3, x4, x5, x6. Okay, not x7. That's how I'm getting the delta x size of the every element. Okay. So if I run this one, sorry, it should be grids nodes. If I run this one, I'm going to get grids nodes. So sorry, grid sizes. I have a typo here. So my grid sizes, since I have a uniform mesh, I have all the element size are 1. Okay, since I have 7 elements, I have the dimensions of the grid size is equal to the dimensions of the elements that I have. Okay, if I type shape, I'm going to get the 7. So number of element is 7, and grid sizes are going to include all the sizes for the given all elements. Okay. Now, another thing I need to know is the coordinates of the grid center. Okay, and that grid center I can learn by grid center is going to be equal to the first set of nodes plus size of the grid nodes divided by 2. Okay, so it's going to be grids sizes. The left hand side of the given element, left boundaries of the given element, plus grid sizes divided by 2. Okay, and if I check this, if I run this, I'm going to get the sorry, so it should be nodes, not the sizes. Okay, if I check the grid centers, so my location of the center points of the given discretization, this one is at 0.5, this one is at 1.5, this one is at 2.5, and the same thing, like continues by increasing increments of by increments of 1. Okay, 0.5, 1.5, 2.5. Okay, those are the information I really need about the grids. Okay, these are the all information about the grids. Now, also I need some information regarding the boundary grids. Okay, I know in this discretization, the first element is going to be the left hand side, and the last element is going to be the right hand side. Okay, so if I add information about the grid boundary IDs, grids boundary IDs. Okay, I'm going to add the IDs of the boundaries located for this given discretization, one-dimensional discretization. Okay, and it's going to be MP array. Okay, I'm going to include that as an array because I want to select the first element and the last element. Okay, and I'm going to also include information the neighbors of that boundaries. Okay, so first one is the zeros element in this given discretization. I have the zeros element here, and its neighbor is the first element. Okay, so I'm going to write 0 and 1. Okay, and the last boundary, right hand side boundary, or this upper boundary is this U6, which is the index is 6, and this one is equal to the basically number of elements minus 1, and its neighbor is U5, which means that it's done it's the 5 is equal to the number of elements plus 2. Okay, so if I do the same thing for this one, for the right hand side as well, basically I will need to take the grids number minus 1. Okay, and then its neighbor is grids number minus 2. Okay. If I run this one, I need to make sure that it's a two-dimensional array. Okay. Okay, now if I check the grids boundary IDs, if I click tab, the grids element has only one property named boundary, so that's why it autofills it, and that those values are 0. So the boundary element is the 0 and 6. Okay, so first entries are the boundary IDs, and the second entries are their neighbors. Okay, for the 0, the neighbor is 1, and for the 6, the neighbor is 5. Okay, now I need to like basically state the boundary conditions as well. Okay, so that's boundary conditions creates a boundary, let's call it boundary conditions, right? Okay. So I showed here the general form of the boundary condition that we have. Okay, the general form of the boundary condition that we have here is shown here. Okay, this is the Robin boundary condition that we are implementing. Okay, if we are implementing the Dirichlet boundary condition, it means that we should set E1 to be equal to 0. Okay, first index should be 1, second entry should be 0, and we should specify the Dirichlet boundary condition. Basically, we should specify the scalar value of the U at the given boundary condition. Okay, this is for the left hand side. Now for the right hand side, we should do the same. Okay, now if we are solving this problem, okay, if we are solving the Dirichlet boundary condition, we should specify the element, okay, boundary condition at the first boundary. Okay, first boundary is the left hand side, and I'm setting the Dirichlet boundary condition. That's why I'm going to set the B1 equal to 0, B0 equal to 1, and I'm going to set F equal to 200. And for the right hand side, I'm going to do the same thing for the B0 and B1, but I'm going to set the F2 equal to 50 because I want to implement this boundary conditions. Okay. Now, again, I'm going to do the same thing with the MP array. Okay. It's going to be a two-dimensional array. And for the first one, I said I'm going to set the Dirichlet boundary condition. So it's going to, the first coefficient is going to be 1. Second one is going to be 0 because I'm setting the Newman the coefficient to be equal to 0. And I'm setting the F value, which is 200. Okay. And for the right-hand side, I'm setting again, the same thing for the boundary condition type, which is a Dirichlet boundary condition. So the 1, 0 is for the Dirichlet boundary condition, 0, 1 is for the Newman boundary condition. For now, I'm only implementing the Dirichlet boundary condition. That's why I'm specifying the 1, 0 for the first two entries. And then the last value is the F value. And for this one, I'm specifying it to be 50 for the right-hand side or upper boundary, in other words. Now, these are the boundary conditions I have. Okay, these are the all information I need regarding the grids. Okay, now let me interchange those locations. Okay, location of this two. Okay, I specified the lower boundary and the upper boundary, and I calculated all the necessary information regarding the mesh. Okay, these are the all information I need about the mesh. And if I run this, I shouldn't get any error. Okay, please numbers. Oh no, it's number. Okay, grids number is 7. Grids IDs is 0, 1, 2, 3, 4, 5, 6. Okay, these are the index of the use. Okay, now I said just make sure that you have the same computation, this computation script in the same directory where you have this test 1D poison. Okay, so the reason is because we are going to import this computation from the from this script. Okay, so if you put it in the same directory, you can call it from the upper part of the script that we are writing right now. Okay, and basically we are going to say that from computation, we know we are going to solve the finite difference solver. So I'm going to call from computation import finite difference as FT. Okay. Now, if I run the script, ideally I shouldn't get any error, and you shouldn't have error as well. Okay. If you are having error, either you misplaced the computation script in any other directory, or you have modified some, maybe the name of the computation script. Okay. If you have kept everything constant, if you are running the script with the line of from computation import finite difference as FT, you shouldn't get any error. Okay. I'm hoping that you are successful in this. If you have any error at this stage, just let me know, because otherwise we'll not be able to use the rest of the code. Okay. Now we have defined the mesh and we have called our solver. Okay. Now, one thing I need to specify about the linear solver, it's one thing is basically, let me show one. So in this, if we implement this equation, okay, this is the Laplace equation. Okay, if we implement finite difference scheme on the given this element, this is the final form of the equation that I'm going to get. Okay, and if I implement to every element, I'm going to get the 7 by 7 matrix. Okay, and that matrix I'm going to call A matrix, and it's going to be multiplied with the unknowns, which are U0, U1, U2, U2, U3, U4, U5, U6. Okay, those are going to be in the X vector. Okay, the right hand side of this equation is going to be equal to B. Okay, which is B vector. I'm going to call this one A matrix, and this one is going to be called B vector. Okay, and I'm going to have X, which is the unknown. I need to solve for the X. Okay, this is the linear system of equation. If I implement this set of equation to every element points, then I'm going to get the 7 by 7 matrix. Okay, because I have the 7 elements. Now, this B is usually regularly filled with the 0. Okay, this is the value of the right-hand side of the equation, or we can generalize it, make it like for the other cases where this right-hand side is not equal to 0, or it's equal to some constant, for example. Let's call it beta. Okay, I'm calling it as a beta. Okay, I'm defining that beta as 0 for now. Okay, now I'm calling. So I know the one thing I know about the B vector is, since I have 7 by 7 matrix on the A matrix, it's going to be like it's going to be based on the number of unknowns I have on the mesh, defined mesh. Okay, if I have discretize the given interval with the 7 elements, I'm going to have 7 unknowns, and those 7 unknowns, 7 by 7 matrix is going to be multiplied with the 7 unknown vector, which is x, 7 by 1, and I'm going to get the 7 by 1 b vector. Okay, I know the shape of the b vector. Okay, so b vector is going to be, I'm initializing this b vector with np full. Okay, and the shape is going to be equal to the grids number. Okay, grids number. We have grids number equal to 7, which means that the b vector is going to be 7 by 1 vector as well. Or like in the Python term, it can be 0-dimensional vector as well. Okay, so the first value is 0, and we don't have second dimension, or actually the first dimension for this b vector. Okay, and it's going to be filled with the beta values. Okay, so all the values are going to be filled with the beta. If it's 0, it's going to be filled with the 0 values. If it's any other number, constant number, it's going to be filled with those values. Okay, let me run the script. If I don't get any error, it means that I have created the b vector with the 0 entries. If I change this beta value to 1, all the values of the b vector is going to be equal to 1. Okay, so this is the right-hand side of the equation. Okay, now I need to generate the left-hand side of the A matrix as well. Okay, that will be done from the computation toolbox. Okay, now if I'm naming the solver, okay, the finite difference is my solver, and I have imported it as FD. Okay, this is the finite difference solver I have. Now I'm just sending the mesh information because it requires the input grids. Okay, and my mesh is grids that I have created. Okay, now I'm running this one. Now, if you check the solver, it should have central function. Okay, implement boundary condition function and mesh information. Just the information, the property that I just sent to the finite difference. Okay, and if you check the solver mesh, okay, it's an object as well, so I can check the sizes. Okay, sizes. I will get the 111, which is equal to the number of elements I have. Okay, so all those mesh properties are attached to the solver now. Okay, it's inside of the finite difference class. Now, first thing, I need to generate the A matrix. For that, I'm going to use the central difference, finite difference. So it's going to be central, and the order of my differential equation is 2. Okay, this is second order differential equation. Okay, so that's why I'm specifying the order to be equal to 2. Now, if I run this one, if I check the solver, I have new, I should have new property, which is the A matrix. Okay, and if I check the A matrix, it's a sparse matrix filled with only 3 diagonal entries. The 3 entries of each row is filled. Okay, if I want to see the A matrix, I can say 2 array. Okay, and I'm going to see the entries of the A matrix. Okay, this is ideally what I'm expecting from the A matrix, where I haven't specified the boundary conditions yet. Okay, boundary conditions are not specified here. I have the A matrix to array is going to be 7 by 7 matrix, where the boundary conditions are not specified here. Okay, I have created the B vector. I have created the A matrix. The second step, the next step is to create the implement the boundary conditions. Okay, so if I implement the boundary conditions, and I should send the B vector because there will be some modifications to the B vector as well, and there will be some modification. Like let me show the B vector as well. Now B vector is not sent to solver yet, so it's going to be separate. B vector is 1 1 1 1, and my A matrix is shown here. Okay, after implementing the boundary condition, you will see that what kind of modification has been done to the A matrix and B vector. Okay. Now, if I run this script now we can check the solver A matrix to array. Okay. If you see, the first entry is changed. Okay. Previously it was -1. Now it's -3 because we have implemented the Richard boundary condition. Okay. And there is no changes on any other value except the last entry. Okay. So first and last entries are modified because of the Richard boundary conditions that we are implementing. Okay. Now, previously it was -1, now it's -3. The same thing for the right-hand side. Previously it was -1, now it's -3. Now, let's check the B vector. Okay. So, first entry is modified based on the boundary condition. The last entry is modified as well based on the boundary condition. So, since we have the different boundary condition, 200 for the left-hand side and 50 for the right-hand side, the modifications are different. Okay. So these are the modifications that we are getting because of the Dirichlet boundary condition. Now, if we now we can solve the problem and get the solution, new solution for the problem. Now, for our case, we are really solving the problem for the pressure. So I'm going to specify it as a P. Let's call it pressure. Okay. Now, the only thing I need to do is just invert the A matrix and multiply the B vector. Okay. I'm going to use the sparse matrix solver, okay, SP solve, and SP solve is going to be imported from the SciPy module. Okay, just make sure that you have the SciPy. If you have run the script up until now, okay, it means that probably you don't have any problem with the SciPy. You have already correctly installed SciPy module. Okay. Now, SP solve. Let me. So SP solve, I'm going to send the A matrix, okay, solver A matrix, and I'm going to send the B vector. Okay. Now I can from SciPy. Let me check the name of the model that we need. Okay. Sparse linear algebra, import SP solve. Okay. That's it. If we run this script, and if we don't get any error, it means that we have solved everything for the pressure. Now, if you check the pressure values, we got the pressure solution, finite difference solution of the Laplace equation. Actually, it's beta 1, which means that it's not a Laplace, it's a Poisson equation. So if we specify the beta equal to 0, okay, we will get the pressure values different than the Poisson equation, slightly different than the Poisson equation. Okay. The only thing I need to do is really to plot this result. Okay. Now I have solved everything at the center of the grid, so I need to make sure that I'm using grid centers. Okay, I need to PLT plot grid centers and pressure. Okay, let me use the scatter plot because these are not the analytical solution; these are numerical solutions. So it's better to represent them with the scatter plot. Okay, and that scatter plot is going to be imported from matplotlib. Plot. Now I forgot the PLT show. That's something important. I forget it every time. Now this is the numerical solution I have. This is the graph. Okay, this is the x-axis. Okay, and this is the y-axis where I'm getting the pressure values. Okay, I specified the Dirichlet boundary condition. Dirichlet boundary condition is 200 at the left-hand side, which is getting there. Okay, my numerical solution is getting there on the boundary. And on the right-hand side, it's 50, and it's getting there as well. Okay. One thing I can do with the plot is to make sure that I'm including the 0 and 7, okay, 0, 7. So if I run this one, so this is my solution, okay, and I want to specify y limit. I want to specify only the lower boundary of the y limit. Okay, I know that my like pressure can be minimum of 0. Okay, like we can't have any negative pressure value, so it's going to be 0 and none on the upper part. Okay. Now this is the pressure result I'm getting. Okay, so as you see, I'm getting almost to the 50. If I increase the number of unknowns by simply changing the grid numbers to 70, for example, I will get the much accurate result. Okay, I'm going to get the 200 on the left hand side and almost 50 on the right hand side. Okay, so this is the numerical solution. Now, how can I be confident about the solution? Okay, how can I check my numerical solver? One thing, I can compare it to analytical solution. Analytical solutions are not available all the time, but for simple scenarios like this, we can have the analytical solution. And in this one we have, and we said that this analytical solution will give us the equation of the straight line. Okay, I'm just copying the analytical solution, and I'm going to upload this script to the BHOS module, the link that I sent. So you can check this link from check the script from that reference link. Okay, so I'm just copying the function which is going to give us the analytical solution. Okay, this is not the numerical solution. This is the analytical solution. Okay, so if I for the analytical solution, I need to specify the x low boundary, x left hand side. I need to specify the boundary condition, and I need to specify the upper bound, and I need to specify the upper boundary condition. Okay, and I need to specify the beta as well. Okay, let me do that as well. Okay, so I'm going to send it, call it after the pressure calculation of the pressure. Okay, now pressure, let's call it pressure analytical. Poisson 1D analytical. X lower is going to be x and 0. Okay, and I need x and 1 as well. Okay.
Sorry for the interruption, but we have some questions in the chat box.
I can't see the question.
All right, so Typhoon Jamal Bailey is asking, why does the pressure decrease linearly?
Okay, it's because of the analytical solution that we have. Okay, so what's the analytical solution of this equation? Let me, if you take the first integral, I got the, my PowerPoint is not working well. Well, anyway, so if I take the first integral of this equation, I'm going to get du, derivative of u with respect to x, equal to some constant. Okay, and if I integrate it second time, I'm going to get u equal to c1x plus c2. Okay, so this is the equation of line, straight line. Okay. So that's why we have the analytical solution is a straight line, and numerical solution, of course, is going to give us the same result. Okay, so that's why we have the straight line. We will make it a little bit more complicated by changing the beta value, and we are going to specify the minimum boundary condition on the right hand side. So that's why I imported the analytical solution as well. So for Typhoon, it's clear. Now Russell, my graph is composed only of 7 dots, not as yours. It's because I changed the grid elements. Okay. Number of grid elements. Now, previously it was grid numbers was 7. Now I changed it to 70. That's why I'm getting the increased number of dots on the plot. Okay. If I change back to again 7, I'm going to get the. Sorry. Let me comment out the analytical selection here. Okay. So that's why, like, if I change the grid numbers back to 7 again, then I'm going to get the 7 dots again. Okay, Russell override. Okay. So Now pressure analytical. Okay. So Poisson 1D analytical. I specified the lower bound and upper bound. Okay. And lower bound is basically the grid boundary condition, the first entry. Okay. I'm going to copy this. Okay. And pass it here. Lower bound. And I'm going to send only the first boundary condition. Okay. Let me click enter and specify the upper bound as well. I'm going to set the second boundary condition, which is the right hand side. Okay. And I'm also sending the beta value, which is 0. Okay. This is the analytical. This will give me the analytical solution. Now, analytical solutions, the analytical solution that we have here is going to export the x values as well. Okay. It's going to export x values and u values. Okay. So I need to have x analytical here. I'm going to get the analytical x and analytical pressure values. Okay. Now, if I PLT plot, I'm plotting this analytical solution because it's analytical solution and it's defined everywhere in the domain. So that's why I'm using the straight line for the plotting. For the numerical solution, I use scatter because numerical solutions are defined only on the points which are where they're calculated, and they're calculated only at the center of the grids. Okay, that's why I use the scatter for the numerical solution and straight line for the analytical solutions. That's something that that's something that will make your graphs more explanatory. Okay. Now XA and pressure analytical. Okay, I'm just going to copy this expression. I'm trying to write like have a full name in order to understand the script when we are going over it again later. Okay. So if I run this one, so this straight line shows the analytical solution and dots shows the numerical solution. They are on top of each other, which shows that my numerical solver works well correctly. Okay. Now, let's change the boundary condition. Let's change the color a little bit, and let's change the color a little bit. Okay, I'm going to have the pressure line, okay, straight line, to be straight like black. Okay, and my scatter plot, I want them to be red. Okay, now if I run this again. And also want to have the labels, because by looking at this plot, I don't understand which one is like, which axis is representative of what. Teacher, will you push this PI file to your GitHub repo, and how can we get recording of today's session? So I'm going to push this PI file to the GitHub, so you will get this script from the GitHub. And for recording, please talk to Togrul. Okay, he's going to provide more information regarding.
Yeah, just a notice on that. This session is being recorded, and I think Javid, teacher, has already gave us his permission for sharing the sessions. So we will be uploading the session and sending you guys the link.
Okay. Okay. So he will share soon. Okay. Now, this is the numerical solution again. We are going to change. We changed the color. Now I want to understand which axis is representative of what. Okay. So I'm going to add the labels. X label is going to be the x-axis. That's the orientation where we're solving this problem, and it's a string, so I'm going to have the quotation marks. And y label is the pressure. Okay. For now, I'm not talking about the, like, usually you should have the dimensions as well, but for now, for this problem, we haven't solved any, we haven't used any, like we can assume that these are the non-dimensional properties, but in general, you should add the dimensions to your plots as well. Now, next thing, I want to add the labels, okay, which will say that the red dots are the numerical solutions, finite difference solutions, and black line is the analytical solution. Okay, TLT label. And you can put the label, I think, like this. Let me check. So it's going to be, first one is going to be the numerical solution, finite difference solution. Second one is the analytical solution. Let me run. If I don't get any error, I got it. I got the error. Let me change this parenthesis. PLT legend. Sorry, its name is legend. I'm sorry. Okay. Now this black line is the finite. So it's vice versa. Scatter is the numerical. Okay. Now let me legend put the legend here. Legend is equal to finite difference. This one legend is equal to analytical. Now I'm just copying this from my cheat sheet. Okay, this is something related to legend, nothing related to the solver, and I'm changing the label. Okay. Now it should have the correct names. Okay. So these red dots are the finite difference solution, and straight line, black line is the analytical solution. Okay. I have full information regarding the graph. Now I will change the boundary conditions. Now, if I change the boundary condition, let's say if I change the boundary condition at the left-hand side, and I make the Newman boundary condition equal to 0 on the left-hand side, okay? So I will basically, on the left-hand side, I will specify this one to be 0, 1, and this one equal to 0, okay? So I change the boundary condition, both analytical solution and for both analytical solution and numerical solution, I should get the same result, okay? And the result apparently is the constant 50 value, okay? If I have the basically defining the Newman boundary condition on the left-hand side, I'm going to have the straight line for the Laplace equation. Now, if I switch to the Poisson equation, and if I change the beta 2 equal to 10, I should get something different than the straight line. And let me comment out this line. Okay. I'm going to see the full solution. Now, it's physically impossible solution because I'm getting the negative pressure values, but we said we are not really solving the real problem. Okay, that's why it's possible to get the negative values, and analytical solution and numerical solution are on top of each other again. Okay, now if I change if I specify the boundary conditions to be Dirichlet boundary condition on the left-hand side with the 200 value, and if I change the condition to be here Newman boundary condition, and I'm specifying the basically u derivative to be equal to 0, okay, I should get the straight line again. No, I'm getting something different. Okay, so on the right-hand side, I'm specifying Newman boundary condition to be equal to 0. I'm getting that derivative. You see my slope is going to go to 0 on the right-hand side. And on the left-hand side, I'm getting the 200. And this is the red, again, is the numerical solution. And straight line is the analytical solution. And if I change the boundary condition, beta value, I'm getting the same match with the numerical solution and analytical solution, which increases the confidence on my solver. Okay, which means that I implemented everything correctly, hopefully. There can be some bugs, and if I find any bug, I'm going to fix those bugs in this BHOS module that you see on the GitHub. And I'm going to upload this test 1D Poisson and also the computation. It's already there, but I'm going to continuously improve it. Okay. If you want to have the 1D Poisson solver, then just use this solver. Okay. This one is basically we can show that this is basically the single phase, steady state, one-dimensional solution of diffusivity equation. Okay, Steady state, because time derivative is equal to 0, we are assuming that the time derivative is equal to 0. And it's one-dimensional because we are only solving for the x-axis. And it's a single phase because when we are solving divisibility equation, it means that we are dealing with the single phase problems. In the multi-phase case, the equation, the conservation of mass, the continuity equation modifies slightly. So that's why we are not solving divisibility equation anymore. If we're solving the divisibility equation, it means that we are solving the single phase flow. Do you have any question? That's all for my part. Sorry. Okay, thank you. Okay, let me. It's not defined. Sorry. Okay, thank you. Sorry. It gives Poisson 1D8 is not defined. So in my solver, I copied this to my script. So that's why in my case it gives the result. In your case, you weren't able to copy it because I haven't uploaded the Poisson 1D analytical to your script yet. After this session, you will be able to run the script. Okay, I'm going to upload both files, and you will be able to run your script as well. Okay. Okay, Rashad, Mr. Javid, I started writing the code from the beginning, but I get error. For example, when I include class breeds pass after enter, I get error. Do you have any indentation before the class? Okay. Do you have any empty space before the before the class grid? Okay. Do you have any empty space before the class grids and parentheses? Rashad.
Just to step in, Rashad Safaraliyev, it would be better if you could share the error message itself rather than where you
Yes.
have the error.
Yes.
Because if it's a syntax error, it's very easy to deal with, or else it might be due to
Probably it's a
some other
syntax error.
error.
It's not a it's not using any, it's not calling anything. It's just creating the object that's named grids. Okay.
Yes,
So
as I can see from his message, there is a white space after the class name greets before the parentheses, which is not
okay.
Python
Yes.
interprets.
That's
That
yes.
might be the problem.
That's true. That's true. You shouldn't put any space between the grids and parentheses. And the version is okay. I mean, you shouldn't worry about your version. How can I contact you if I have any questions? I mean, you can, you can get my contact information, I think, from Toro, but well, you can email me. Okay, that's the best way, I believe. You can email me. I mean, you can use my. Let me type my. I'm checking my boss email. Are you a boss student? Typhon, is Typhon boss student?
I think no,
Okay.
but he can
Well,
still contact you from your BHOS email, so that should not be a problem.
this is my boss email. Okay. Do us. Okay, Rashad, just check. Javid Shiriyev boss edu. If that's the boss address I have, if you don't get any reply, send me email to my Gmail address. Okay. I shouldn't have any typo in the email address. Okay. So much. Sure. This is my email address. You can contact me from my email address. Okay. Any other questions? So basically, we solved the single phase, steady state, one-dimensional problem. Okay. We use the finite difference solver. And I'm going to like after this, even after we are done with this session, I'm going to continuously improve the BOSPy model, so you can continuously check the BOSPy to see other features that we are going to add to it. Okay, so that the motivation here is to create the BOSPy in the first place, and then to improve it to make it robust and competitive as well. Okay. Any other question?
All right. If you guys don't have any questions, thank you Javid teacher a lot for this session, for sharing your knowledge and also demonstrating the analytical solutions and the theory in Python code. I hope this was a very informative session for all of you guys. And stay tuned in our Telegram group and follow our social media pages to stay tuned with every update happening. We will be holding this specific part of the petroleum engineering course each Saturday at 3 p.m. Uh, and yes, Leoford Caribbean. Uh, we will be taking the attendance sheet from here, and the certifications will be determined based on how much of the sessions and how many sessions in total you have attended. Again, thanks a lot to our speaker. You,
Thank
you guys can contact him through the emails mentioned in the chat box. This chat will be available throughout the course. And hope to see you in our next session. Thank you for joining and good luck in your future endeavors. Thank you as well,
Thank
dear
you.
speaker.
See you next time.